Welcome to the fourth session of the Biohazard workshop. Today we have two talks, one from Alex Watson and one from Gabriel Amselem. I'm not sure how to pronounce it, but perfect. Yes, so we start with the talk of Alex Watson from University College London, who will talk about growth fragmentation and quasi-stationary methods. Please, Alex.
Thank you very much, Aline. And thank you to all the organizers for this really nice meeting. I'm glad to finally be here. I hope we can do something in person sooner rather than later. So I will talk about growth fragmentation models, and this is going to be quite a mathematical talk. We'll be focused on some sort of mathematical methods for proving things about the long-term behavior of these growth fragmentation models, and sort of fairly new techniques for doing that. And this is all joint work with Denis Villemonnet, who is in Nancy and is probably known to many of the audience. Okay, so I'm going to start with just a totally so simple, intuitive explanation of what I mean when I say growth fragmentation. So a growth fragmentation model is a model for a collection of cells. They can be real biological cells, or it could be something more abstract than that. But the important thing is that they have some sort of, each cell has some size associated with it, and we're tracking the evolution of the sizes of those cells. So we start out with a single cell with size X, and as time progresses, the cell size increases in a deterministic way. So it follows this ODE, X dot equals tau X, and so that represents the growth of the cell as it takes in nutrients or does whatever. And then at some random time, with exponential rate b, which can depend on the cell size, the cell divides or fragments. It produces two daughter cells which have random size themselves. So in this picture, one cell has size y and one cell has size xt minus y. The size of the first daughter is chosen according to this kernel kappa, which again so it's a random thing which potentially depends on the size of the parent cell just before birth, just before division. Okay, and then those cells go on to lead independent lives as well. So say this red cell does the same thing, increases according to this ODE, and then divides. And the yellow cell maybe does something different. Maybe it increases a bit and then it dies. It just gets killed with some exponential rate. So this is the general growth fragmentation model, and the thing that I'm going to study, one of the things I'm going to study is what I call growth fragmentation process, which is this bold ZT, and I get that just by looking at this whole collection of cells, looking at those ones that are alive at time t, and collecting those up as ZU of t, where U is some index set that I'm not going to worry about. Okay, and ZT is just the set of all those sizes, or the collection of all those sizes. Okay. So that's what I'm going to look at, and the talk will be about this. Actually, it will be about a slightly coarser version of this ZT, but I'll get there in a second. And I'm just going to, I guess, pull out two sort of special things about the model that I presented here, which is I've got here sort of binary division. This is not an essential feature of the model. It makes life a bit easier sometimes, but in general, I won't need that assumption. And the other thing that's present here that won't be necessary in general is this mass conservation, right? So y plus xt minus y is xt. So there's, in the picture I presented, there's no loss of mass or loss of size or whatever you want to call it at division. But again, that's not a necessary assumption, but it does make life a bit easier sometimes. So we will occasionally want to assume that. Okay. So what do we want to learn about these things? It's easy enough to write this down, but asking and answering questions is a bit harder. What I hope to see in these sorts of models is I hope to see some kind of what I would call equilibrium behavior, although this isn't quite isn't a totally appropriate term. So I'm going to show you now just a simulation I did just with some arbitrary coefficients that I picked out of thin air, and we'll see what happens in the long term to this growth fragmentation process. So I start out with a single cell of size whatever, x at time 0. Sometime later, it grows. So after 4 time units, seconds, hours, days, I've got 100. 2 time units later, I've got 500. 0.7 time units later, I've got 1,000. So you can see this sort of rapid increase in the number of cells. And you can see as well from this picture that I've not only got more cells, but I've got sort of a big variation in a big variety of sizes present there as well. So this is just a simulation. So I've got access to all of these things. And if I just plot a histogram of these sizes, I can hopefully see something. So here at 100 cells, I've got this, it's fairly rough. At 500, it's sort of looking a bit smoother. At 1,000, it's looking even smoother. And so you can imagine here, you can guess that the cell sizes should be sort of settling down into some kind of asymptotic profile of the size distribution. And that's the thing that I'm trying to approximate with this density fit in red. Okay, so that's one side of things, is the distribution of cell sizes, and the other side of things is the number of cells. And this we expect to grow exponentially. So I plotted here just log of the number of cells against t, and you can see a roughly linear fit here to that. So what we sort of guessed from our simulation, and what I describe as this equilibrium behavior, is that ZT should be roughly exponential in the number of cells, and it should converge to this asymptotic profile times some constant maybe that we will think about as well. Okay, so that's what I hope to see. It doesn't have to happen, obviously. It could be, in principle, that the division is very fast and the growth is very slow, and so the cell sizes sort of get smaller and smaller and smaller because of the division, and you get sort of attracted to 0. Or the opposite could be true as well, that I grow quite fast and I divide quite slowly, and the cell sizes get attracted to infinity. So this is not sort of necessary behavior, although it is, of course, pretty much what you would expect in a realistic situation. And so this whole talk is going to be about how to prove something like this, and how to find conditions on the coefficients, the growth rate, the division kernel, the division rate, and the death rate that allow you to observe this behavior. Okay, so I said so now is the bit where it's going to get a bit more mathematical. I'll try to give pointers along the way for people who might not be familiar with these methods, and so I'll try to indicate the meaning of everything that I'm doing here. But we are going to now delve into some more mathematical representations of these things. So like I said, I'm going to look at a slight sort of coarsening of this thing. So I'm not just going to look at Z. I'm going to look at something a bit weaker, which is a sort of average over Z. So I define this thing TTF. This is going to be a semigroup. I define TTF of X to be the expectation started from a single cell of size X. And I look at all of my cells at time t. I compute f of z, f of their size. I sum those up, right? So that's put into the expectation. So what you can think of here is, if f is sort of the indicator of a set of some interval a b, let's say, then TTF is going to be the expected number of cells alive at time t whose size lies inside AB. So it's a sort of expected version of the picture that I showed in the previous slide. Okay, so how can I describe this? Well, the dynamics that so far I don't know this exists at all. That's going to be part of the problem. But the dynamics that I described in the first slide give the following description. So if I look at differentiating this thing in time, I can describe that using an operator that basically gives a mathematical description of what I talked about earlier. So this first term here, this tau x f prime x, this is saying that an individual cell is going to grow according to that ODE with tau. So it's going to grow with rate tau. This second term here, this integral, comes from the division. So k is kappa x dy plus kappa x minus dy. So this is sort of looking over that division event, and that division event produces not just a cell of size y, but another one of size x minus y. So I sort of average out those, and then I multiply by 2, which is the number of cells produced, and bx, which is the division rate. Okay. So this k here is sort of representing the rate at which a cell of size y appears due to fragmentation, due to division of a cell of size x. And so that's why you see this sort of plus f of y means I'm getting a cell of size y added into the system. Okay, and then big K is B plus D. So this is the growth rate plus the death rate, sorry, the division rate plus the death rate. And so I've got minus KF because that means I'm taking out, so at rate K, I'm taking out a cell of size X. So that's the sort of explanation of this thing. And now the question for me as a mathematician is, well, given an operator like this, is there actually, so given this A and given tau and K and big K, is there actually any T that satisfies this equation? So this isn't totally obvious. You know, you might think, yeah, for sure, I can just write down the big cell system that I did on the first slide, and I write that down mathematically, and I take expectations, and I get the answer. And that sort of works, but there's you have to be a bit careful, and I'll explain why. So that sort of is the existence of that thing. And then the other question is the uniqueness. So do these equations actually characterize T, or could there be other cell systems that give rise to the same equation, and therefore this needs something extra in order to fully describe the cell system. And a particular question here is, what does this suitable F mean? Right? Is that going to have an impact on the uniqueness? And the answer is yes. There's something a bit interesting that happens there at the boundaries of the near zero and near infinity. Okay, so if we can establish that, if we can find the existence and uniqueness of these things, then I've got a good way of describing the evolution of my cells, and I can now ask the question: what is the long-term behavior like? Do I see the thing that I saw on the previous slide with the simulation, where I get exponential growth in the number of cells, HX some kind of residual dependence on the initial conditions, and nu the asymptotic profile of the cell sizes? And at what rate do I see that? So how fast does it happen? Right, so those are going to be our big questions that I'll address in this talk. So there are a couple of existing approaches that you might know if you know something about this field. Some mathematical approaches to this. So one of them is a sort of spectral theory approach, where you treat this A as a sort of operator on some space of functions. If you're good at functional analysis, this is a great way for you to tackle this problem. You treat this operator as just some kind of operator on a Banach space or whatever. You look for eigenfunctions h and eigenmeasures nu, which are positive, and you use some relative entropy methods to get the convergence that I said. It works great if you can do it. If you're good at functional analysis, then this is a very nice approach, and there are very, very good works that take this approach and find good conditions. I'm a probabilist, so I try to do as much as I can with probability. So I'm going to avoid this approach as much as possible, but it is effective if you can do something with it. You know, the difficulty, you might be looking at this and saying, well, yeah, it's just Perron-Frobenius theorem. Like I learned that in third year functional analysis. Yeah, but A is not compact or self-adjoint or any of the nice things that you assume when you're in third year of undergraduate. So it is really difficult, and you need to do a lot to make this work. And second approach would be like this. If you can do the first part here, right? So if you can find an H that satisfies this equation, then actually there's a strong connection then between A and a certain Markov process. And then you're in the world of probability, which again I like a bit more. And you can then start to say, okay, well, if this Markov process is ergodic, that means it converges to some kind of stationary distribution. And then you can get that convergence again using the Markov process convergence. So you can sort of convert T into something about a Markov process, use the established Markov process theory, and get the convergence that you're after like that. And again, that works well if you can do the first step, right? So if you can find H, then that works very nicely. And that's a long established method. And a third possible approach is the sort of Harris type ergodic theorems for non-conservative semigroups. This is some very recent work actually by Bansai and others, many of whom are in this call. And this is a sort of Lyapunov function type approach. Essentially, you sort of mimic the way that the Lyapunov function, so if you're a specialist, you understand this, if not, then fine. But you sort of mimic the way that Lyapunov functions work for conservative semigroups, but you allow for the fact that you may actually have growth of this thing. And so the size of this TT, the total mass of the TT, if you put in f equals 1, is the expected number of cells alive at time t. Right? So this is growing in time, and that's why you have this non-conservativeness that means there's more to do there. That's a very nice new approach, and again, you can do stuff with that and get very nice results. What I'm going to talk about now, and I'll explain in a bit more detail in a moment, but I'm going to sort of do an approach that's sort of intermediate between the second and the third. So what we're going to do is we're going to try to guess H, but we're going to get it wrong. And we're going to not make a connection with a Markov process, but with a sub-Markov process, with a killed Markov process. And then we're going to use Harris type theorems. So we're going to use this Lyapunov approach, but we're going to do it for semigroups that are non-conservative because of killing rather than non-conservative because of growth. And so instead of the mass of the semigroup increasing, as in the third point, it's decreasing. And it turns out that you can do something very nice here as well. Okay, so before I go on, I just want to say quickly, again, for specialists, there is sort of an alternative approach to, or alternative way of writing down this equation, which is if the TT can be expressed like this, so if you can write TT as the integral of some UTY dy, and K is sufficiently regular, then you can actually, so this UTXY represents the density of cells of size Y at time t, given that the initial cell had size X. Yeah? So you can actually write down a differential equation for that density, and I see this a lot in the differential equations literature. This is the way that people prefer to write this down. You know, the thing I'm studying and this thing are not quite equivalent, but they're sort of almost the same. So I just mentioned that in case you're looking at this and thinking, oh, isn't it the other way around? That's what's going on there. Okay. So our approach, just recap this again, we're going to make a link with a killed Markov process by taking this A and doing some kind of picking out some kind of trajectory inside of the cells. The killed Markov process is not going to have a stationary distribution because it's killed, right? So as time goes to infinity, the probability of killing goes to 1, and you're not going to get a stationary thing there. But there is an approach that uses quasi-stationary distribution. So basically with this, you sort of condition on not dying up to time t, and you look at where your Markov process is, and then you take t to infinity. And that gives you a quasi-stationary distribution. And it turns out that that is then linked back to the asymptotic profile for the growth fragmentation that we started with. So we're going to do everything with this Markov process. Basically, we're going to prove existence and uniqueness of that thing and show when it has a quasi-stationary distribution, and then we'll make the link all the way back to the original semigroup, to the original thing that I was interested in. So that's the basic layout of the proof. So I'll start to give some results here, first of all, about the existence and uniqueness, which turns out to be harder than you might imagine. At least it's harder than I imagined. And I'll start by explaining how we get the connection with the killed Markov process, because that's really the central approach that we make. Okay, so this is the point where things are going to start to get a little bit technical, but it will come out of this again. So if you get lost, then take a nap, and there will be some less technical stuff towards the end as well. So okay, alpha and beta are some parameters that I fixed here, but I can vary them later on to find good conditions. And I define this function v. So this is going to be a kind of biasing function that will allow me to pick out of our big collection of cells, that will allow me to pick out a single trajectory. And so let me explain a little bit about what's going on here. So we've got alpha and beta, so we've got sort of a different power depending on whether x is bigger than or less than 1. And this weird integral here of 1 to x dy over tau y, this is actually the time that it takes the growth part to go from an initial cell of size 1 up to the cell reaching size x. So this is kind of like a hitting time for the growth part only, right? Ignoring the fragmentation, only looking at the growth part. That's what that integral means. And of course, the other one from x to 1, that's starting from a cell of size x and growing to a cell of size 1. Okay, so that's sort of why this v is useful, because it has that strong connection with the hitting times, with the growth part. Okay. So given this, right, given some choices of alpha and beta and the v that we define like this, we're going to make a new operator which is going to give us our Markov process. Okay, so I present this in this sort of technical way, but I'll explain what the Markov process is more intuitively on the next slide. So we take A and we compute A of FV and divide by V, and then we subtract off BF. So B is a constant. So we're doing sort of here, we're doing a sort of biasing procedure with this FV thing. And then minus BF is we're producing some extra killing. And B here is the supremum of 1 over V AV. So you can see from this, if I plug in F equals 1, you can see that L1 is going to be less than or equal to 0, because then I've got 1 over V AV times its own supremum. And that tells me that rather than having growth, I've now got killing, right? So I'm now generating something that is killed, whose mass decreases, or is at most conservative. Okay. So how can I understand this thing? Well, if I just write down the equation that I put on the previous slide, and I work through moving things in and out of the integral and trying to get it in a nice form, I can describe explicitly the characteristics of the Markov process here. Right, so it's a Markov process with a growth rate tau. So just like before, I follow the ODE x dot equals tau x. The integral part is now no longer representing division, but rather jumps of this process, because now I have a single cell, I have a single process, I don't have division anymore, I just have jumping down, which came out of division originally, but now is just a jump. So KV, which I'll write down in a second, is the jump rate from size x to size y of this Markov process. And I also have a killing. So Q is a killing term, which removes the Markov process, so kills it off and sends to some symmetry state at rate Q. Okay. Excuse me. So KV is just a sort of biased version of the original K, and you can show that this is sufficiently finite that you can really write this down properly. And Q you could write down as well, but I haven't. It's just a bit ugly. It's not sort of mysterious, but you can write it down in terms of K and big K and tau. Okay, and now we have this equation, which looks much uglier now that I read it than it did when I wrote it. So what's going on here? So on the left, we've got a sum. We've got our expectation over the cell system. Okay. And we're sort of looking at this thing and we're picking out in a biased way a cell or we're sort of biasing our choice of cell that we look at and then taking expectations over that. And we're doing an extra killing here as well. So that's what we've got on the left. And on the right, we've got something nice. It's just an expectation over the Markov process, the single Markov process. And so this, if you like, is a kind of many-to-one theorem, which tells you that there's a connection between the big cell system and between the Markov process that we've written down. And what we're saying here, and the intermediate thing is the relation, is the thing I'm actually interested in discovering. What we're saying here is there's an intuitive description of X, which is as follows. I take my big cell system, so imagine that this graph here is a graph of the sizes of every cell that's alive at every time in my big system of cells. and I pick out a trajectory. So I follow a single trajectory instead of following all of them. Okay, so I start at time 0 with size x. I only have a single cell initially, so I follow that. The bold one is the bold line is the one I'm following with x. I follow that up until the division event. When the division occurs, I have, in this case, I have 2 cells with size y1 and y2. And I pick a cell of size y with probability proportional to vy. And so I pick I pick the cell of size y1 with probability vy1 over vy1 plus vy2. And the same thing for y2, of course. So in this particular instance, I've picked out this first cell. Okay. So I'm making a biased selection of the children at each branching event. That thing goes along, and say at this branching event, maybe I pick the second of the children, and this goes along, and at some time I see a killing of this thing as well. Now, this killing could happen, suppose I followed this cell and I got killed, and that cell got killed in the process. That's one way that killing could happen, but it could also happen because of the extra killing that I've introduced by this BT thing here. Okay. And so that's pretty much a description of the meaning of X. So hopefully this convinces you that there's some kind of, I'm doing something, it's not just a mathematical trick, right? I mean, it is, but at the same time, it has a meaning in terms of all these cells as well, in terms of a sort of tagging of the cells. Okay, so that's X. So now I've got a Markov process, and now I'm going to do my best to work with that and to prove things about that and to transfer those results into results about the growth fragmentation. Okay. So I have to make some assumptions. Let's leave these for now. If I make those assumptions, then I can prove that there is a Markov process X on the state space 0 infinity union D. This D is a symmetry state. So once I get killed, I get sent to D and stay there forever. And I can describe it with the following equation. So QTF of X is the expectation X fxt. This is me writing down this just says L is the generator of X. And the L here is exactly the same as on the previous slide, except I've sort of introduced this D now. So instead of just vanishing when killing happens, it actually just gets sent to D instead of going away. Okay. And we can show that this holds for a suitable collection of F. And even more than that, Q is actually the unique semigroup that satisfies all of these equations. And so there's only one semigroup with this generator. Or there's only one Q that fulfills all of this. Okay, so you might be thinking now, how would I construct this, right? How, I've been very vague up to now, and I've really been saying, okay, well, intuitively you got this cell and it grows and it divides and I take expectations. Okay, but now is the point where we should be a bit more precise. So I'm going to give a couple of proof ideas. I'm still going to be pretty vague, to be honest, but hopefully you should get a bit more of an idea of of the important things here. Okay, so it's easy enough to construct X, right? All you do is you say, okay, I'm going to start with X. I'm going to follow my differential equation, X dot equals tau. It's going to increase a bit. It's going to jump according to my rate KV that I've written down explicitly. Okay, it jumps somewhere. And then it's got a new position. And now I follow the ODE again, and I jump, and I follow, and I jump. And at some point, I get killed as well at rate Q. Well, that's very nice, and it worked perfectly well. You have to check that there's no accumulation of these jumps. So it could happen in principle that you jump, and your jump times accumulate, and then you don't know where to go after that. So it turns out the only way that this can happen in this model is that you jump down to 0, basically. So your jump rate is unbounded near 0. And so our assumption, this was on the previous slide here, this KV x0x, this is the total jump rate at size x. And we just assume that this is bounded near 0. And that prevents that from happening. So that means you're never going to get attracted to 0 by a collection of jumps. And that allows you then to construct, that gives you the existence of X. You do a bit of work, which is fairly standard, to check that X is the unique solution of a martingale problem. Again, if this doesn't mean anything to you, this is all sort of the technical details here. And And the thing that's really hard here that I was really surprised by is proving the uniqueness of this thing. So it's not hard to show that the martingale problem has a unique solution, but what we wanted to prove was that the semigroup, so this Q, that there's a unique solution of the semigroup equation. And it's much harder than we thought. So if you have a diffusion part, it's actually very easy because it has kind of a regularizing effect. But if you just have the deterministic growth and the random jumps, it's difficult. We couldn't find any existing result that does this. I tried. I read Effie and Kurtz. I really did my best, but we had to write our own proof here. And so what this takes up more of the paper than I would have liked. So what you can do is you can show that if you take a solution of the semigroup equation, it does correspond to some kind of Markov process. You can show that that Markov process doesn't approach infinity or zero. We have kind of a super martingale type argument there. And then you need to show that that solution is actually a solution of the martingale problem as well, which is not obvious, right? What else could it be? You ask yourself, but it's not obvious. And once you do that, then you can use the uniqueness of the martingale problem solution, which is okay. But yeah, we really had to go back to basics for this proof. So there is something here which I didn't appreciate before I started this work. Okay. All right, so given that, so suppose now we know everything about this Markov process, now we get the theorem about the growth fragmentation, which is what we really wanted. Right? So remember this A from before, we've got the growth, we've got the division here with K, and we've got the removal from division slash death. dA, set of suitably differentiable compactly supported functions, and the function V, which was our biasing function from before. And the result is there's a unique semigroup that satisfies, okay, this is just dt, the TTF is equal to TTAF. I've written it in integral form. There's a unique semigroup that satisfies this equation for all f in this dA. And moreover, we can write it in terms of our Markov process. And so you just take a Markov process x, you look at f of x over v of x, multiplied by v of the initial size and multiplied by e to the bt. You're sort of doing the unbiasing in the spine motion, and you're adding the branching in again with sort of a combination of the dividing by v and the multiplying by e to the bt. And so the thing that I want to highlight here, which again I think is really necessary, I don't think it's just a byproduct of the proof. You need this function v in the domain of A, right? So you need this equation to be satisfied for f equals v, and not just for f compactly supported. And the reason somehow is that v is not compactly supported, right? V does something at 0 and at infinity. And so you sort of need to know what happens at the boundaries in order to get uniqueness. It's not enough. I really think it's not enough to just know what happens in the center of the state space to get uniqueness of this equation. Obviously, V, maybe you don't have to have V itself. You could have something that's sort of comparable to V, but you need something there to understand that, to get that uniqueness. All right, so that's the big theorem. And so, you know, if you're not a mathematician, then you're looking at this and thinking, well, okay, you just proved that you're talking about something real. And that's a fair sort of criticism. But for me, this was the first step that we really needed to follow in order to say anything at all, in order to talk about anything. And so it depends on this killed Markov process. And that's not just, you know, that's not just sort of a weird technical thing for doing this weird technical proof. It's also central to our method for proving things about the stationarity, about the asymptotic profile. So it will come back in the next section. Okay. So long-term behavior. What we hope to see now is some kind of exponential growth in the number of particles and some kind of convergence to that asymptotic profile of cell sizes. What can we do here? Well, again, we're going to do everything we can using X. Okay, so we went to all this trouble to find X. Now we're going to use it for the long-term behavior. A really nice paper. So if X is a killed Markov process, killed at some time TD and sent to the symmetry state D at that time, a very nice paper of Champagnat and Villemonnet in on 2018 onwards gives Lyapunov type criteria, which I'll specify a bit more precisely in a second, that ensure that the killed process X has a quasi-stationary distribution. And again, here this is more precise about what I mean by quasi-stationary. Right? So I take my process, it's killed at TD, I condition that I haven't been killed yet, and I look at the behavior of X. Right? I look at where X is, and I take T to infinity, and that gives me this new X. This thing is called the quasi-stationary distribution, and this is what I use to describe the long-term behavior. And they even show more than this, right? They show that this happens at exponential rates, so this happens very fast. And so just to hammer home this connection, right? This sort of analogy between the killed Markov process and the branching process. Right? Our Markov process is killed at a random rate, so the probability that there's something there is decreasing, or if you like, the expected number of things there is decreasing from 1 down to 0 as time increases. And the thing that we're interested in has branching at random rates. So the expected number of things there goes from 1 upwards as t increases. So they're really analogous objects, but it turns out that there's a lot of, well, because of this nice paper and previous work by other people, there's a lot of nice results for doing things with quasi-stationary, with killed things, and there are fewer nice results for doing things with increasing mass. So this is why we looked at this. And obviously also because Denis is the co-author on this stuff, and he knows this stuff inside out. Okay, so here's the theorem. I won't talk very much about the proof because it really is a translation of the quasi-stationary results about this spine. So okay, this slide is just going to be assumptions. So okay, two assumptions to start out with. What do these say? The first one says, okay, look at those y where there is a positive probability of branching into a cell of size x. This is what this is saying. And the assumption is that for every x, that set of y has to have positive measure, or this integral has to be positive. Okay. So this is sort of saying you can always get back to 0x, right? You can always get close to the origin, no matter how far away you are right now. That's the first assumption. And the second assumption is this one about a sort of lower bound for k, and this is sort of the opposite thing in a way, which is saying that you can there's sort of a set of things that you can always reach from moderately sized cells. It's that there's sort of a lower bound, so you're not sort of, a thing that would violate this would be if you could sort of only jump to you could only jump to smaller and smaller cells as x increased in this interval, or something like that would violate this assumption. But this is sort of a lower bound on that branching rate. Okay, these two look very technical, but what we use them for is to prove a sort of irreducibility for x. So we're sort of saying, okay, you can get from any place, from any state to any other state in sort of not too long a time. It's a sort of irreducibility, or like a Dublin type condition, if you're familiar with these things, and that's what we use these for. Okay, so it really stops you from segmenting the state space, right? from having totally different behavior in different parts of the state space. Okay, assumption 1 and 2, and then the third assumption is the really critical one, which is about Lyapunov functions. So we need the existence of these Lyapunov functions psi and phi, where a psi is less than or equal to lambda 1 psi times plus c times indicator L. L here is a compact set. This is the thing that you've seen before for Markov processes. So this is really expected. You can it's a function that says that you can get pulled into the center of the state space. That's the interpretation of this. And then for phi, we have a phi is bigger than or equal to lambda 2 phi. You can think of this phi as being like a sort of sub-martingale function for the cell process. It's sort of, yeah, I don't have really a good intuitive description of this, but this is the function of this. And some other conditions that ensure that these things play nicely with each other and play nicely with V as well. So those are assumptions. If we have all of those, then we can prove the following theorem. There exists lambda, nu, and h, and some positive gamma, such that e to the minus lambda t, ttf, converges to hx times integral f d nu in total variation norm at exponential rate. And this psi quantifies dependence on the initial size. And moreover, we can characterize h and lambda and nu with these equations that tth is equal to e to the lambda th and nu tt, so this means starting in nu tt is equal to e to the lambda t nu. And this is the connection with that spectral theory stuff that I was talking about at the very beginning. Okay, so this is what we're hoping for. Convergence, so exponential growth of the cell number, convergence of the empirical measures of the cell sizes to some kind of asymptotic profile. And again, here this h, this is explaining the residual dependence on the initial size of the cell. Okay. All right. Okay. So I'm going to transition now into some sort of future outlook and discussion type things that we might want to talk about later. But this is the main theorem. You might be looking at this and thinking, okay, there are a lot of assumptions there. Can you really prove anything at all? And the answer is yes. So we're working on this actively at the moment. So this is all a bit preliminary, but I'm just going to show you on this slide some simple assumptions where you can really show that everything works. I don't claim these are the best assumptions. I don't claim even that they're better than what the existing literature can do. But these are just this is some example where things work, and I'll walk you through this quickly before we go on to future stuff. So assume that K breaks down like this. So basically, the branching rate depends on X, but the place you branch into, so the size of the daughter cells, or the relative size of the daughter cells, does not depend on X. So we've got some measure P here, which represents the relative size of the offspring relative to the parent. Okay, this is called self-similarity sometimes, or sort of separability condition. We assume that P satisfies this moment equality, which is the conservation of mass. It says that on average, you don't lose mass at fragmentation events. And also this equation for tau represents that you can enter from 0. So for example, if tau of x is equal to 1, which means you have linear growth of the cell sizes, then you can enter from 0. That satisfies this condition. If you had tau of x equals x, which means you have exponential cell growth, then you do not satisfy this condition. So you can start at 0 and enter positive masses. Okay, if you have this conservation of mass assumption, you can pick phi to be equal to the identity function. If I work out a phi, then the branching part goes away because of the conservation of mass, and you just end up with this tau x over x, which you need to lower bound in order to get the assumption in terms of lambda 2 from 2 slides ago. You can actually pick psi to be equal to v, the original biasing function, and this entrance from 0 means you can put alpha equals 0. This is a little bit irritating to explain, but if you remember, v included this integral, right? So it makes sense that there's some kind of relation there with that entrance behavior. And now I'm going to pick really specific coefficients just to show that you can do something. Let P be 2 times dr. This is just uniform binary repartition. So you split into 2 cells at every fragmentation event, and you pick the size of one offspring uniformly, and you assign the rest of the mass to the other one. That's that. Allow tau x to be equal to big O of x as x goes to infinity. This is pretty much necessary anyway in order for the growth not to explode. And then if you have this equation, this is a balance equation between the growth and the fragmentation. So we need 3 plus square root 8 times the lim sup of tau x over x is less than the limit of k as x goes to infinity. And this is saying that the growth near infinity is weaker than the fragmentation near infinity. If you have those assumptions, then everything works. Okay. And really, this is just, you use these Lyapunov functions, you plug everything into A, you move things around, you bound things where you can, and you get the result. Right? We have some results as well when you don't have this entrance behavior. So when tau x looks like x, we have some stuff as well. But yeah, this is just to demonstrate that there really is something to do here. Right? I don't claim that anything here is optimal, but I think it's I couldn't push this any further with our method, so I think this is sort of optimal for us. Whether or not it's optimal in general, I'm not sure. Okay, all right. So that's the long-term behavior, and I want to talk now about just some perspectives for the future. I just sort of wrote down 4 slides of just things that I'm interested in, and I'd be interested to discuss these in the discussion session at the end. Nothing precise here at all, just ideas and things I found interesting recently looking at arXiv. So, okay. First of all, computation. So if you actually want to do something, so everything we've done has been existence, right? It's going to be, okay, there is some asymptotic profile, but that's not really good enough if you want to really apply these things. And so the first thing that you might want is to actually compute this asymptotic profile, right? And there's a very nice approach given to you by the quasi-stationary distribution. So this is called a Fleming-Vieira process. If you take a bunch of particles and run the killed process, the killed spine on them, when one of them dies, you put a new particle back in and you put it at the average position of the remaining particles. And then you look at the empirical distribution of the particles, of particle sizes. That should approach the quasi-stationary distribution. This is a sort of well-established algorithm. There's a few technicalities. I mean, you know, I haven't proved anything about this particular process, but it should work very generally. And so this should be a way of computing this thing. I haven't tried it, but I think it should work. It might be an interesting thing to have a go at. It definitely works for other types of branching process. So Denis, as well as Andreas Ciprianu, Emma Horton, Alex Cox, a bunch of people at the University of Bath have been doing this for the neutron transport problem, which is a related branching process type problem. And it works very well there. So that's an indication there should be something to do there. This is also quite linked to sequential Monte Carlo, if you've looked at that before. Again, I'm not an expert, but it works pretty well. Okay, so that's the asymptotic profile. What about H and lambda? Here I have a bit more difficulty. I'm not quite sure what to do. Some previous work that I did suggests that this method should work. If you define a function L of P like this, so you take your Markov process, I've actually unkilled it, so I've removed the killing here. And you compute this expectation over cycles. So Tx is, you start from size x, and you grow and split and grow and split and wait until you see x again, right, until you reach x again. If you look at this integral over those cycles, this thing, so lambda minus b should satisfy LP equals 1, right? So it should be the unique p that satisfies this equation. Because the minus q is sort of the killing, right? And the p is the random killing, and the p is the deterministic killing that you're looking for, or a deterministic approximation of the killing rate. And so there should be something here that allows you to get lambda. I tried it, right? And I had an undergraduate student working on this year. And if you just implement this sort of naive Monte Carlo estimator for this, so you just look at you just compute a bunch of those cycles for the Markov process, and you try to find the p that satisfies this, you can do it. I mean, it does work, but the variance is very high. And I'm not sure exactly why that is, apart from Monte Carlo methods have high variance. So I'm not quite sure what to do about this. So it'd be interesting to think about some sort of variance reduction techniques or alternative approaches that could work here to sort of exploit the spine process in order to find something about lambda and h as well. Yeah, so that's the only idea I have there, but I think there should be something to do here. Okay, moving on. Some extensions of this work. What else could be done? Well, one thing that I sort of slid.
I'm sorry, Alex. I have to. I guess you are near the end, but
yes.
if you could just, yeah, you have, I don't know, 3-4 minutes. Or...
Yeah, no problem. I will do. So something sort of unclear, something that I hid here a bit is that I was looking at expectations everywhere. And it's quite interesting to try and do this not for the expectations, but for the process itself. It should also work, right? Some recent work on this that I've done as well. I'm probably forgetting some other people here, but I think there should be something interesting here. What if you have diffusion, right? Actually, the existence and uniqueness get easier here, but you have other problems with the behavior near zero. So there is something sort of interesting here to do potentially. And there's a recent paper that looked at this in some specific cases. And this question about attraction to mass at zero is sort of a bit open still. So you could easily imagine that there could be some cells that get killed off by being attracted to zero and then sort of die there, and that you still have something sensible to say. In principle, quasi-stationary stuff can handle this case, but it's not obvious, right? It's a bit harder. And I think probably this will be my last slide then. So some really interesting, I just want to highlight some interesting recent work on growth fragmentations with types, right? So some work by Cloès da Saporta and Roger looked at having old and new cells. So when you divide, one of the cells gets called old and one of them gets called new. And this type influences the growth rate and nothing else. So the old cells grow at a different rate from the new cells. And a really interesting result that they found is that it's actually preferable in terms of the overall rate of growth of the number of cells. It's preferable to have distinct growth rates for the old and the new cells. It's better than having the same growth rate. And I just find this really interesting. And I think there's maybe some kind of connection with optimal control here. So I sort of know this a little bit from insurance math stuff, but maybe there's something there, some connection there that could be exploited with the spine. 2 more bullet points on here. Interesting work as well by Marguet and Smardy last year about a sort of branching process inside a branching process. If you sort of embed a CSBP inside a growth fragmentation, the motivation here was a parasite population that lives inside a population of growing and dividing cells. This paper studied the long-term behavior of this, and I thought this is just very, very nice, interesting thing. And this, in general, this sort of typed growth fragmentations, it reminded me a bit of the viral load thing we talked about last week. And obviously, it's not directly analogous, but there's some similarity there as well, which might be worth exploring. And then finally, a paper by Caligara and Roberts from this year called Spatially Dependent Fragmentation Process. They have a window, right? They have a geometric window, and they allow it to fragment horizontally or vertically. And obviously, a long, thin window will fragment more because you've got all those vertical lines that can hit it, will fragment more than a square window. They don't have growth there, but I thought there was something sort of interesting there in terms of the typedness of that thing. Okay, and I've said enough, I think. So I just leave you then with this reference here. Okay, this is still in preparation, so you don't have a real reference to follow up, but hopefully that will be done soon. We're working on the final pieces, and yeah, just remains for me to say thank you very much.
Thank you very much, Alex.